So let's start. So last time I finished at this point when we declare a data type using the GAT syntax. Every field can be made either linear and non-linear. The default, and what you'll see with types that were defined before linear types existed, is linear. This linear function is converted to a multiplicity polymorphic function for backwards compatibility. Now, what happens if you use the unrestricted version? Well, in this case, the constructor has a more restricted type. It's marked as the general function, an unrestricted function, and this means it's harder to use it, right? If you use a linear constructor, then you have some guarantees, but with the unrestricted constructor can be used in less contexts. However, there's a trade-off. If you use such a constructor, it is harder to use it, but it's easier to pattern match on it. The point is that when you pattern match on this type, you can pattern match on it linearly, and this argument will be brought in an unrestricted context. I will explain this in a moment. For now, I'll show you an application of this. Let's suppose I'd like to carry. Well, let's write simple carrying first. Actually, that's uncarrying, and it compiles. What if I'd like to change the type of this uncarry to take a non-linear B? Well, this doesn't compile anymore. What I could do is I could make the resulting function unrestricted, but now I kind of lost information because this original function was linear in A, and this function is no longer linear in A. So what we need is a tuple which specifies that some elements of this tuple can be extracted linearly and some cannot. And we can do this by modifying this type. Let's say I have a pair B, and I change the type of the constructor to this one. So now this constructor to use pair, you need to provide B in an unrestricted context. It means this argument has to be non-restricted, but A can be treated linearly. So you can uncarry this function, and if I try to give stronger guarantees, that will still work. But if I try to weaken the guarantee, if I try to put the dot here is important. If I remove it here, I'll get an error. Okay, so data types have their multiplicities, and if you would like to, you can even have a multiplicity polymorphism here. So that would mean that this you can have either pair 1 AB or pair omega AB. However, there are several issues with the current implementation, so I will not be using this. Okay, I'd like to show an important data type, and I'll call it unrestricted. To construct an unrestricted value, you just construct it linearly. So this is kind of the identity constructor. The difference is that in linear types, linearity is a default. The unrestricted constructor is wrapping its argument, but it's giving a promise that this A is unrestricted. So I can convert now. Think of this carrying. Here I was carrying a function with 2 arguments. Let's suppose I have only 1 argument, and I'd like to wrap it using the unrestricted type. I will take now a general function, and I will convert it to a linear function from unrestricted A to B. Okay? And you can go back. Okay. Now this is interesting because I think this can be in there. Yeah. This is interesting because I take a general function a to b and I convert it to a linear function from unrestricted a. So you can think that general functions, those are that are not necessarily linear, are really linear, but they are taking this unrestricted type. Okay? So imagine I removed from Haskell this data type altogether. You cannot use the arrow. Instead, you can use only the linear arrow. Well, everything would break, but you could convert everything by adding this unrestricted thing everywhere. Okay? So what you can think here is that we are extracting an effect from Haskell that's already there. So I'll show you an example in the following way. Suppose you have composition. Any two functions can be composed. And I'd like to make those functions impure. Impure only in the, not literally, because I/O is pure, but I will do this. Okay? So what I'm now saying is, and this can be implemented using the bind operation. And if I'd like this to be a primitive in Haskell, how would this look like? Well, if you look at this type, the only thing that this function can do is take this a and pass it here. Okay? So this is composition of impure functions, but I could simplify this combinator by taking out this a. Right? And I'll also flip the order of arguments. I'll put I/O first. And you recognize this type as, this is bind, right? So let's do something similar on the unrestricted type. I'd like to write, I start with unrestricted b to c. I have unrestricted a to b. And I'd like to get unrestricted a to c. Well, this function is returning a c, but the only way it could get this c is by passing unrestricted b here. So we could simplify this combinator just like we do it with I/O, make it return unrestricted b instantly. And this combinator, this function, is known as extend. It's a common-add function. Okay? So while I/O is put on the right-hand side of the arrows, and it means that a function is kind of impure, it has effects, unrestricted can be put on the left-hand side of a linear function and say this function can duplicate its arguments. So this is a common-add. Like a monad, but with all its arrows reversed, the dual. Just like monads have return, common-adds have extract. With the I/O type, it's easy to get in. If you have an integer, you can always make it an I/O integer, right? However, it's hard to get out. If you have an I/O integer, you won't get an integer out of that, right? With unrestricted, it's the other way around. If you have an unrestricted value, it's easy to get out. But if you have a general value, there is no general way to make it unrestricted, right? In a linear fashion, because that would mean that you could cheat the restriction of linearity. If you have this composition. Oh, and maybe let's implement this extract. Unrestricted. Okay. If I have this bind type, I can simplify it further by assuming this function's identity. In other words, that B is equal to IOC. Then I will get a different combinator. And how it's called? This is joined, right? What happens if I do the same thing here? I'll assume that B, that the function given is identity. So what I will get? I'll get unrestricted A. I'll get unrestricted A to unrestricted A. And this is called duplicate in a common net. So let's try implementing this. Duplicate. We take an unrestricted value and we'd like to make it unrestricted. Well, that looks easy. We have an x and we know it's unrestricted, so we could just say unrestricted x, right? The problem is this doesn't work. This unrestricted thing is unrestricted, so we could write this only if we had this arrow, but we don't have this arrow. Well, the solution is that we need to unpack this x. We say unrestricted x, and the difference now is that this x, even though we are in a linear function, we can use this x in a non-restricted way. So now I can say unrestricted of unrestricted x. Okay? So unrestricted is a common nut, and you might think just like impure functions are those arrows. Are pure, just like you can say that I think that impure functions are like pure functions, but they have this I/O on the right hand side. It's called Kleisli. The nonlinear functions are really linear functions with this unrestricted thing on the left hand side. So they are called Kleisli. And that might remind you of categories. So categories are, when we add this type, this arrow type is a category. And linear functions also form a category. And if you have a category, you might now wonder what is an isomorphism, what is product, what is coproduct, right? You need to revisit all those libraries and rethink how do things change when you introduce linearity, right? So one thing to note is that there is a notion of isomorphism. Two things are isomorphic when you can write two functions that convert between them, right? I have type t, I have type u, and they are isomorphic if I have a type t to if I have two values u to t and t to u that are mutually inverse. Now it looks like unrestricted and A are isomorphic. Right? And this compass. Right, but this is not linear. So A and unrestricted A are isomorphic in the category, in this category. Okay. However, they are not isomorphic in the category where we enforce the motion, where we enforce the arrows to be linear. So the notion of isomorphism is more fine-grained. It makes more distinctions if you introduce linearity. What happens to products and coproducts? Well, the thing is, if you have arrows, you can define what does it mean to have a product and coproduct, like a sum.
So only the first isomorphism is not...
No. An isomorphism is a pair. You can't call this an...
The first map is wrongly defined now. The second one...
No, this one is well defined, this one is not.
Yeah, exactly. Okay.
So, what does it mean to have a product and coproduct? Well, the definition is more complicated, but I'd like to simplify it a bit. A product, if I have two types AB, the product is a type TAB such that we have projections TAB to A and TAB to B. There is more to that, but this is a necessary condition. Likewise, the coproduct is a type, so I'll call it T, is a type T prime AB, such that we have injections A to TAB and B to TAB. Okay, so it's kind of the same, except the arrows are reversed. Now, what sorry, that should be T prime. Yes. In normal Haskell, what are products and coproducts?
Tuple and either.
Right. So for product, we can just take tuple and take FST and SND here. For coproduct, we can take either. This will be left, and this will be right. Now, is there a problem here with linearity?
Sure, you're not consuming D.
So the problem is with product, right? Coproduct makes sense because I can say left x equals left x, and that works. Even that works, because left is multiplicity polymorphic, so I'm just instantiating it to a specific type. And I can do the same thing with right. But if I try to do this with first, the computer won't let me. This is not linear. So what's the solution here? Do we really lose coproducts? Do we really lose products? The answer is that there are products. However, they are more complex. There is a different way to multiply types than taking tuples. And that way is visible only when you have linearity. And I'd like you, there is an anecdote that's often repeated when introducing linear types. Think about a vending machine. A vending machine takes a coin, and let's say it will give you either tea or coffee. Okay? This is a vending machine number one. So how does this work? You insert a coin, and let me make this type linear. You insert a coin, and you get either tea or coffee. This machine is the one who's controlling what you will get. You don't have a choice. You just insert a coin, and you need to be able to handle both getting a tea and a coffee. Right? Now, what happens if I say tea, coffee here? You get both, right? Because a tuple has to be, you have to consume both parts of the tuple. So this is a vending machine where you insert a coin, but you will get both tea and coffee.
It's better.
Well, remember that we are now thinking about resources. If you could arbitrarily dispose of tea and coffee, that would not be a problem. But if this coffee would be, let's say, a nuclear bomb, right? Now you have a problem because you can't just drop it. So it means that getting a resource is a two-edged sword, right? You get it, but you now need to do something with it. In normal Haskell, in the nonlinear Haskell, you have it and you are happy. There is a different product, and this product is not available directly in the prototype, and I will call it prod. A prod tea coffee is a product which is either tea or coffee. You can pick which one of those, but you can pick only one. So this is the normal vending machine you will find. You insert a coin, and you get a product of tea and coffee. You don't get either tea or coffee, because that would mean the machine is making the choice for you. You get both, but you can pick only one. Right? You are getting a box, and now you can press either I want tea or coffee. How would you implement such a machine? Well, that machine has to be prepared for both converting a coin to tea and for converting a coin to coffee. The either machine could only use one of that, But to implement this type of machine, you would need both. So if you have a product, then this first thing can be implemented. Okay? Although you, of course, you would use a different syntax, but this would now be linear.
So this is the linear product.
So this is called additive product.
Additive.
Yeah. And this one is called multiplicative.
So are you basically composing a linear function with a non-linear function to add the...
No, everything is linear.
Everything's linear?
Yes.
Okay.
It's just you need to, creating this product is different from creating a tuple.
Right, okay.
To create this product, you need to be able to answer two types of requests. Give me an A and give me an B. But you're right? So if I notice that this function is not linear, I cannot I cannot just duplicate things on right?
So how is the double primed first? How are you getting away with ignoring the second element of the tuple if that's linear?
Because this is not a tuple. This is additive product which behaves differently than a tuple.
Can you draw the data or define the data type for prod?
No.
Okay.
However, I have three replies here. So let me finish this diagonal thing. This is non-linear. You cannot have this, right? But if this is product AA, then you can have this. Because now you are it's like a machine. If you have a machine that gives you T, it can give you a product of T and T. In both cases, because you would only be able to pick one. This is not this won't let you magically clone T, right? Because you can, while you have a product, you can pick only one of those, one of its elements. What was the question? I'm sorry. Oh, can I implement? Yes. In short, no. However, there are three workarounds. First of all, if you'd like to have a product of the same thing twice, this is actually a function from Boolean to A, right? Because if I have a function, a linear function, well, it doesn't matter. It's if I have a function from Boolean to A, and that argument is given me linearly, the only thing I can do is I can call it once, and that's as if having a product of A and A. If we had dependent types, which means the type of this thing could depend on what Boolean value I gave there, we could simulate the general product of A and B by saying I get this X, and my return type is if X then A and then A else B, right? But we don't. The answer number 2 is that the difference between additive and multiplicative product can be considered to be the difference between data and co-data. In Haskell, when you define a data structure, what you say is how can you create an object, right? This is a data type with two constructors. If you'd like to create such a data type, it's easy because you just use a constructor. But if you'd like to pattern match on it, then it's harder because you need to consider all cases. A co-data declaration, which is not there, however, there is a fork of GHC which has experimental support for co-data, is different. A co-data is defined by saying how you deconstruct a product, an object. So this is a co-data object, and if you have an X, it's easy to deconstruct it because you call one of its destructors. So if I have an X, I can get an integer, I can get a Boolean. But how do I construct an X? Well, I need to do co-pattern matching in the sense that I need to specify what will be the responses to every one of those requests. Okay? And if we had co-data, we could say co-data product AB where FST is product AB to A, and SND is product AB to B. So there is Haskell gives you only data, and if you think about it, functions behave like codata, but we don't have general codata support. Linear logic is more symmetric than classical logic, and this product type is one reason. There are some dualities that are hidden if you don't use linear logic. I'm not sure if I'll get into this, but this is one example. So there's data and codata.
Simulate code data in Haskell using ranking types, but
yes. Oh, sorry. Yeah.
Not linear setting, but can you do that in a linear setting?
Yes. So yeah. So I gave you two ways, and there is the third way. So one way is if you have prod AA, then you can have it. Then you can have a product by using a function. The other way, yes, if we had code data and we don't, we could write it this way, and I guess that would be the best way. The third way is to encode it. It looks like this. Or should I have either AB? I hope I didn't mess it up. I'm sorry, this should be either A to R or B to R. Okay. So this is an alternative encoding that uses rank types, and it also works. And if you'd like to, you can write as an exercise just the projection functions. If you put dots everywhere, those projection functions will be linear. So this is kind of the Morgan's law, because this either type is dual to the prod type. And those arrows work kind of negation. You know that negation of something is like that thing implying falsity. So while normal, classical, the Morgan is and or are dual, linear is that prod and either are dual, and the other pair is do and par are dual. Par is another data type that's pretty hard to define, so I won't go into it. In linear logic, you have product either, you have two types of products and two types of, two ways to say or. The unrestricted type is the exclamation mark. It also has a dual, the question mark. I'll list references later. Okay, so that tea and coffee were resources. What if we are not dealing with resources? We'd like to deal with information that can be freely copied. Well, this is the unrestricted type. how can we create a value of type unrestricted? Well, we have the constructor, but we'd like to do it, create it linearly.
Classify the choice.
Hmm?
Classify the choice. Like that. I don't know. I'm confused. Sorry.
So let's suppose you'd like to apply a function bool to unrestricted bool. Well, booleans are not a resource; they are just information. How can we say that? How can we convert a linear boolean that cannot be duplicated to one that is? Well, we use pattern matching. Oh, yes. Okay. So, although you cannot write f prime x equals unrestricted x because that consumes x non-linearly, you can say you can pattern match on all constructors of a boolean and say that it's unrestricted after all. Likewise, while you cannot say fx equals x comma x, that's non-linear, what you can do is you can pattern match on false and true to get the same thing. Right? So this way, in a sense, you are saying explicitly saying we are not sharing. This false could be a different false. Right? The Haskell notation, this notation, enforces that this x is shared. If it's a big complicated structure, only the pointer will be copied. Only the pointer will be passed. And if instead of a boolean we had a very complex maybe of list of something, then we would be copying everything. That would be linear instead of constant time. So that pattern is pretty common. It's called movable. And to be movable means that you can create an unrestricted version of this thing in a linear fashion. And what we have here is an instance of movable for bool. Okay. Likewise, how would we write an instance of movable, let's say, for either? Right. In general, this is not possible. What you need is movable A, movable B. So if we'd like to move left x, then we can use move of x of this instance. So now this value has type unrestricted A. We need unrestricted of either AB. So we need to, okay, so this has type unrestricted A. This has type unrestricted B. We'd like to have a value of type unrestricted either AB. How do you do that?
Fmap.
Fmap. But now we'll run into a problem. There are two problems. One is that unrestricted is not a functor, but I can say deriving functor. There is another problem. Fmap, the function in the functor class, is not linear, right? So what I need to do is I need to say fmap prime And that works. Okay. Likewise, how would you write an instance for tuples?
With the same concept. Either.
You know, you need like an applicative for tuples.
Right. So I'm giving move x, y. And what I can do is I can say move x, I can say move y, but that's not good because this gives me unrestricted A, unrestricted B, while I want unrestricted of a tuple, right? And that's applicative. So I write a pairing function which takes unrestricted A, unrestricted B, and gives me unrestricted AB. Pair unrestricted x, unrestricted y equals unrestricted xy. Hopefully that should work. Okay, now let's say move xy is equal to pair move x, move y. Okay. How about instance movable unrestricted A?
Just duplicate.
This is duplicate. And if you think about it, unlike the previous cases, we don't need this. Unrestricted is always movable, right? Because we already know the values unrestricted.
For the pair example for tuples, is it possible to write a generic applicative, or does it need to be specialized to pair?
The funny thing is, if you have a functor and if it has this function, you can also get the applicative from it. There are two ways to define applicative functors, and one is to say f of AB to FA to FB.
Oh, you can turn from the tuple with another f.
But
Yeah.
there's also the way of saying, and this is called a monoidal functor.
Cool.
Right? And you can convert between those two. Now with linear types, there are some variants, whether you put dots here as well, right? And this requires careful library design. Okay. How about movable for lists as the last example? Well, yes.
But with
Yes.
yes.
So if I have an x, and if I try to, well, I need this, again, we need a linear version of map, which I defined earlier, I believe. Yes, we need this version of map, map L. So I need to map L move x, and is that good?
No, you get a list of.
Right, that's a list of unrestricted. Okay. And we want unrestricted A.
Foldable.
I think that's traversable.
Traverse, yes.
Oh shit, yeah.
Is this the correct signature for traversable?
That's sequence.
No, that is for sequence, not for traverse.
Yeah, you need the.
Yes. In fact, traverse is going to do both map and
You need. Yeah, you need.
sequence.
Yeah.
Hmm?
I mean, you can compose that with your mapl to get.
Right.
figures.
I have to compose it.
Yeah.
So what I was trying to check is that you notice this. And here is the point where we need the applicative thing. So we would need to be saying lift A2 ness x and trxs, right? Except we don't have lift a2, so I'll write it down. Lift a2 equals, I hope I didn't mess it up.
You didn't call it
L.
Right. Yep. So we got a few types that are movable, and what types are not movable? Well, I don't think I've shown you any. Functions are not movable in general, because there is no way to duplicate, because what you would have to duplicate is the logic inside a function, perhaps some closures, and that's not possible in general. So you can't write an instance of movable A, movable B to movable arrow, AB. Abstract types and polymorphic types are not like you can't have a general instance movable A. It needs to depend on the type. Finally, when you get to linear APIs, you can have a type such as movable array A, and this is also not doable. In some cases, we explicitly want things to be resources, and then they cannot be movable because we would be violating the promise of the API we are trying to build. One more thing about unrestricted and movable thing is that in Haskell, operations like plus and multiplication are not linear. So if you'd like to add two numbers in a linear way, what you could do is you could write an instance for movable for int, or that could be provided. And once you have movable instance, you can always add things and multiply things just by saying move first.
Would there be performance penalty for using move?
Yes, unfortunately, because move creates a pointer, wraps it around. What you could say is a new type. Unfortunately, new types have to be linear. So if you say new type x equals x int, this is linear, and so your next try might be into x. However, due to theoretical reasons, you can do that. So if you'd like to wrap a linear value in that unrestricted container so that you can use it multiple times, you have to use a data type. And GHC could simplify it using case of non-constructor, but this is not guaranteed, right? We are counting on. Yeah. Okay. Now, I've mentioned multiplicity polymorphism, that you have a value of type A.mb, right? We already know that a normal arrow B is equivalent to unrestricted A linear to B. Right? There is a more general version of the unrestricted type. It takes a multiplicity. So this is a new data type that is a generalization of unrestricted, and it looks like this. Previously, we had here this arrow, and now we have the multiplicity polymorphic arrow, which looks like this. In particular, identity, the identity wrapper which does nothing, you obtain it by giving m, setting as m identity, sorry, as m1. This means that this will be the linear function. If you put omega, you will get the unrestricted version, which is this type. So this is a common generalization of wrapping things in an identity box and in an unrestricted box. A different way of looking at this is that in normal Haskell, values have type. In linear Haskell, values have type and x have multiplicity m. Right? If you bind a variable, if it's linear, then it will have multiplicity 1. If it's omega, if you bind a variable in a normal function, it will have multiplicity omega. If you bind a variable in a multiplicity polymorphic function like this, it will be a variable. Now, just like you could say that every linear function is a function from, every nonlinear function is a linear function from an unrestricted thing, then you could say that every multiplicity polymorphic function is a function from this mult type. So, in a sense, what we are saying is that this, instead of thinking that every variable has a type t, we're saying every variable has type mult mt, and every function is linear. So in that sense, we could collapse the two concepts to one, even though they are on the surface they are different. Time out.